This video is going to be examining the differences between theoretical and experimental probability. So the formula that I have here is probability of success or probability of success. So you can say this form is how we should write it when we're using shorthand notation, or if we're using mathematical notation. So that, in other words, this just means exactly the same thing as probability of success. To determine the probability of success, what we do is we take the number of desired outcomes, so the number of outcomes that we can actually get, over the number of total outcomes overall, so the number of total possible outcomes. So let's look at the example of flipping a coin and landing on heads in this particular case. Now, the probability, this is how we should write it mathematically, probability of landing on heads, okay, or you could write it in words, probability of landing on heads, is equal to the number of desired outcomes. Let's have a think first. On a coin, there is a heads and a tails. We want it to land on heads. How many heads are there on a coin? Just one. So we're going to put 1 right there. And we're going to divide that by the number of total outcomes. How many possible outcomes can we get when we flip a coin? 2. So the probability of landing on a heads is 1 out of 2. Or if you'd like to calculate this as a decimal, this is 0.5. So the next instance is rolling a dice, or that should say die, and landing on a 4. So let's write this mathematically. The probability of rolling a 4. You could say rolling a 4, or you could just say probability of 4, just as long as it's written in some sort of logical manner. So let's have a look at the probability formula now. The number of desired outcomes. So if we look at the die, a die has numbers 1, 2, 3, 4, 5, 6. We want the number 4 to roll up. How many times does the number 4 roll up on the dice, or the die? 1. Out of how many possible outcomes could we roll on a die? Well, there are 6 options on the die, because you can land on 1, 2, 3, 4, 5, or 6. So that is our probability, and we can't simplify this down any further. However, we can express this in a decimal format as well, which is approximately 0.167, and I'll just put recurring decimal there. 0.16, not 167, 16. Next question is, choosing a random student from a class of 24. Probability of choosing a random student of a class from 24. So the probability of choosing from class of 24. So again, how many possible outcomes are there? Well, there's 24 students in the class. And how many students do we actually want to pick? 1 out of a possible 24. And so 1 divided by 24 equates to 0.0416 recurring. The last question is choosing a red card from a deck of cards. So probability of choosing a red is equal to, this one's a bit different, because now if we imagine a deck of cards has 52 cards in them. But how many of them are red? Half of them are red. So in this case, we have a total of 26 out of 52 cards that can be chosen, because 26 are red, 52 are in total in the deck. This simplifies down to 1/2, or again, this simplifies to 0.5. So now that we've covered our idea with theoretical probability, let's quickly move on to experimental probability. So it says here, calculate the following for the spinner on the right for 100 spins. So, theoretical probability. How many possible options can we get out of this? Well, for one spin, we can get 1 out of a possible 4. 1 out of a possible 4, 1 out of a possible 4, or 1 out of a possible 4. Okay. And for each of these spins, if we calculate that, if we spin this 100 times, we would then expect to see each of these rolls happen at least, or theoretically, 25 out of 100. Now some of you might be asking, where did I get the 25 from? What's 100 divided by 4? Oh, sorry, what's 1/4 of 100? That should get you 25, and that's where I got 25 from. The only difference is that when we look at things theoretically, they don't always match up experimentally. So what I'm trying to say is, if I actually spun the spinner 100 times, would you expect me to get 25 out of 100, 25 out of 100, 25 out of 100, 25 out of 100 for all these colors as we theoretically predicted? What we're going to do is we're going to have a look at the actual simulation. So I've got a spinner here. The spin is pretty much exactly the same thing. I am going to spin this 100 times. So we're going to do 50 plus another 50. And let's have a look at the results after we've done this. Oops, sorry. The results show as such. So green came up 19 times. So green came up 19 out of 100 times. Blue came out 27 out of 100 times. Red came up 30 out of 100 times. And yellow came up 24 out of 100 times. Now, what we're going to do is we're just going to quickly calculate this because as a decimal, so we can have an easier comparison of the actual magnitude of numbers. If you type this into your calculator, or if we just use the idea that 30 divided by 100, we move the place values, and that ends up becoming 0.30, 0.27, 0.19, and 0.24. If we compare these experimental probabilities to the theoretical probabilities, you can see that this does not match up. So this happens 0.25, this happens 0.30. So 30% of the time, 25% of the time, 27% of the time. The point I'm trying to make in this video is that sometimes when we have a theoretical probability, it does not match up to the experimental probability because of the fact that it's a pure experiment, and sometimes our predictions don't always hold up to what we predict. So it's not necessarily that experimental probability is bad, theoretical probability is good. It's just these are the concepts that we have to keep in mind when we're thinking about experimental probability.